Stanford University.
So hello everyone, welcome to CS 193P lecture 19. Today we're going to be talking about OpenGL ES on the iPhone. Yeah, okay. So before we get started, a couple quick announcements. So the final projects are due a week from today. So that's Tuesday, March 16th at 11:59 p.m. We're going to need from you your code bundle, as well as a couple PowerPoint slides or Keynote slides that you'll be using during the final project demos, and then, of course, a README sort of describing what it is that you did. We will hopefully have an email out about what exactly those things are later tonight. Okay, so also we have final project demos on March 18th. They're going to be 12:15 to 3:15 p.m. in Hewlett 201. We're going to have 2-minute presentations in a sort of a rapid-fire setting. When you run out of time, you get off the stage whether you finished your material or not. And we are going to be recording these for iTunes U. So if you are planning on putting this up on the App Store and you don't want to tip your hand, let us know and we'll cut you out of the recording for iTunes U. Okay, so any questions before we move on? All right. So today I'm going to be talking about OpenGL on the iPhone. And this lecture is sort of motivated by the fact that there's a lot of material in OpenGL. It's a very deep subject. And so if you just go onto the internet and start looking for information on how to do OpenGL, this is sort of what you end up getting. There's sort of two axes here. There's sort of beginner tutorials up to advanced, and then there's general OpenGL tutorials, which generally talk about the desktop, down to OpenGL ES on the iPhone specifically. And so if you look for these things on the internet, this is what you tend to get. It's either really beginning stuff for the desktop, or up to advanced, or it's advanced stuff on the iPhone, which assumes that you already know a lot about OpenGL. And that's not super helpful if you're wanting to be down in this category. So that's really what this lecture is about. I'm assuming no knowledge of OpenGL, and I'm only really touching on it because it's such a huge subject, we can't really, get you into the entire, you won't learn how to make a full application out of this, but it's hopefully enough to get you started and know what's possible and know where to look for more. Okay, so today we're just going to be covering just sort of a general overview of what OpenGL is, coordinate systems and transformations between them, drawing geometry into your scene, using textures to make that geometry look more interesting, and then finally some other details about the differences between OpenGL on a desktop and on the iPhone. Okay. So OpenGL stands for Open Graphics Library. Essentially, it's nothing more than a software interface to whatever particular graphics hardware your machine is running. Because it's implemented in hardware, it's actually very fast and is able to quickly render 2D and 3D graphics. And generally, it's meant to be hardware agnostic. So if you're running your OpenGL code on a Windows machine, it should run equally well on a Mac, assuming you're not delving too deep into the OS-specific stuff at the higher levels. But the low-level stuff, like saying drawing a triangle, that should run the same everywhere you go. That said, that's not entirely true on the iPhone. So the iPhone doesn't really run OpenGL. It runs a version called OpenGL ES. The ES stands for Embedded System. And this is actually a subset of OpenGL that's a little bit more limited in functionality, but is able to get away with almost everything you'd want to do and have a power savings while you're doing it. Now, this is actually very important because the normal utility libraries that you find in OpenGL, like glut and glue, are not available in OpenGL ES. And this is the reason why 90% of the tutorials you find online aren't going to be helpful to you. So if you ever see anything that starts with glut or glue, it won't work on the iPhone. Okay, so OpenGL is a C API to what is essentially a state machine. So how many of you guys have taken EE classes and learned about state machines? Okay, not very many. So basically what a state machine is it's an abstraction for describing how a machine should work. There's a bunch of states that it can be in. Usually you represent them as sort of little bubbles. And then you have transitions between states. And the machine behaves differently depending on what state it's currently in. So if it's in draw triangle mode, it's going to draw triangles. If it's in draw line mode, it's going to draw lines. And so every call to OpenGL is somehow either changing the machine state or issuing a command. So most of these things are enabling or disabling features like, say, depth testing or whether or not you're doing texture mapping, or it's going to be issuing a drawing command, which is going to end up changing the frame buffer that gets displayed on the screen, or it's going to be reading back state in some way. But the vast majority of them are actually changing the machine state so that it's in whatever appropriate mode, and then actually issuing the drawing commands that are going to display something to the screen. Okay? So now, a whirlwind tour of coordinate systems. So does anyone know what a coordinate system is? We want to venture an answer?
Let's just say RN.
RN? OK. RN is a coordinate system. So a coordinate system is basically just a way of parameterizing space. So you can think about it in say in the maps application, right? We take the sphere of the Earth, and we give every position on the Earth a set of numbers that is associated with that position, so latitude and longitude. And the coordinate system also has an origin, which is at 0 latitude, 0 longitude, which is somewhere off the coast of Africa, I think. But it's completely arbitrary. It's just a way of describing locations. So we can also build a coordinate system in this room. I can say that this corner of the screen right here is 0, 0, 0. And as I go up, I'm going to say that increases in y. As I go, say, this way, that increases in x. And as I go this way, that increases in z. And so I can say, OK, where my hand is right now, that's, I don't know, about 2 feet x, 3 feet y, and 3 feet z, right? And I can move this around, and it all works. But I could just as equally well say that Josh's head is the origin of our coordinate system. And it really doesn't matter. It's all just sort of an arbitrary way of breaking up these spaces. The reason why this is important is because graphics hardware is very good at transforming between these coordinate systems. The whole point is that you're taking these vertices that you're defining in some space and finally converting them into window coordinates, so you'd be able to actually draw something on the screen. So accordingly, OpenGL has a ton of coordinate systems. And there's sort of this onion of coordinate systems where you have one set of coordinates, which is a transformation of another, which is a transformation of another, which is a transformation of another. And the whole point is when you're coding in OpenGL, you're setting up these transformations from one set of coordinates to another. So let's start digging into this onion. So on the outermost layer, we've got window coordinates. So you should already be familiar with these. These are essentially the device space pixel coordinates. So when you get touch events in your iPhone, these are in window coordinates. So the top left corner is 0, 0. And as you move down to the right, you go up to the full resolution of the screen, which is the 320 by 240, right? OK. So OpenGL doesn't really care about this, though. It's more concerned with what it calls normalized device coordinates. So as far as it's concerned, the screen is a unit square centered with the origin in the middle, and it ranges from -1, -1, up to 1, 1. So anything that's drawn outside of that is going to be off the screen and won't show up. Now, this is actually not just a unit square. It's actually a unit cube. So if you can kind of imagine that you have a cube where the front face of the cube is the screen of the phone, anything that's drawn has to be within this volume. Otherwise, it's not going to show up. An important thing to notice here is that we have the x-axis kind of going to the right on the screen, the y-axis going up, and the important part is the z-axis is coming out of the screen. And that matters when you start defining transformations and rotations and things like that. OK. So the next layer of the onion is what's called the clip coordinates. This is sort of hard to draw, and honestly not all that pivotal to you as an OpenGL programmer. Essentially, this is the step where it cuts out any geometry that isn't within that bounding volume. So most of the time, you're going to be working with I-coordinates. So now we no longer have this sort of canonical unit cube that we're looking at. We're actually instead looking at a perspective space. So this is more obvious. We look sort of through it. So for the first time, we now have this sort of a notion of a camera. So the camera is the origin of the system. That's this floating origin out here. And you can imagine if you draw a line from the origin through every corner of the screen, you sort of build this pyramid coming out from the eye. You see that? OK. So if we extend this pyramid through the screen out some distance, and then we consider the space between the screen and the back of this pyramid thing, we get a shape that's called a frustum. Okay, so this is this pyramid truncated thing where the front face of this frustum is the screen of the phone. So everything in the world has to be within this frustum or else it's not going to show up. Okay? Cool. And the reason why this matters is because this is how you get perspective effects. So when we transform this into those normalized device coordinates that we saw before, we actually just take sort of the back end of this frustum and squeeze it down, which means that things that are farther away get shrunk more, which is why things that are farther away look smaller. Okay. So the next layer in this onion is world coordinates. So honestly, world coordinates don't mean anything. They're purely a user construct that people use to define how they're breaking up the space in the world. So whenever you, it makes it easier so that way when you create an object, you can say, I want it to be, all of my objects are relative to some fixed location, like the corner of the screen or Josh's head. That's just an arbitrary distinction as to where things are. And it doesn't actually have any meaning in the OpenGL universe. It's just a construct. The next real step, though, is object coordinates. So object coordinates are it's the coordinate space in which the objects are actually defined. So when you say draw a triangle at this position and this position, this position, you're usually doing it about some origin, and then you translate that object around to put it into world coordinates. So this is all kind of a lot to take in 3 minutes. So it'd be a great time to stop for questions, and I have a demo coming up to maybe make this a little bit more clear. So you guys have any questions? Yes?
Why was it a unit cube? How is it sure that it would be a square?
How is what sure that would be a square?
Initially, you showed that the device coordinates were a unit cube.
Yes.
How is it a unit cube?
Okay. So you're saying this is a unit cube, but how do we know that this is?
Map to the device. It's not symmetric.
Okay, so you're saying there's an aspect ratio mismatch. Is that what you're getting at? Okay, so yes. So what you're saying is the space is a cube, but the front face of the iPhone is not a square, so something's messed up. And you are exactly right. If I draw something that goes from -1, to 1, 1, it's going to come out stretched because OpenGL doesn't care what pixel aspect ratio you're using. Okay. So I think that this will be the very first thing that comes up when we get to the demo. So why don't we head to that? Are there any more questions? Okay. Okay. So what I have here is a very slightly modified version of the OpenGL ES template project that you create with Xcode. Almost all of the code that I'm going to be showing you is in the ES1 renderer.m, and almost all of the action is taking place in the render method. So this is the thing that gets called every 30th of a second or so. It depends on how the timer is set up to actually draw the screen. So the part that we care about is here, which is where we're actually setting up the transformations to go between those different coordinate systems. So what I have here is sort of the most basic set of transformations you can use. We're not changing anything from object coordinates all the way up to normalized device coordinates. So if you run this, we end up getting exactly what you said. We have a unit square that's actually ended up being stretched to fill the whole screen. So it's no longer preserving the aspect ratio that we had before. So unfortunately, I can't actually show you what happens if we try to have an empty transformation from the normalized device coordinates to the window coordinates. So this GL viewport command is the thing that actually sets up that transformation. So you go from the unit square to whatever pixel coordinates you actually happen to be using. So if I comment this out, we're going to end up just getting a gray screen, which is less helpful. But we can mess with it a little bit. So suppose rather than having it fill up the entire screen, I want to have it only go halfway up. Now it only fills half the screen, and it squashed it down to fit the aspect ratio of the viewport that I gave it. So OpenGL doesn't really care about the size of your pixels. It just basically scales everything to fit into whatever space you tell it to fit it in. Okay. So usually you're not going to be messing with viewport. If you would, you might want to have, say, two separate views of the same scene so you can change the viewport within a single OpenGL context. It's probably not that important for anything that you're going to be doing. So that's how we go from device coordinates to window coordinates. Now let's look at going from eye coordinates to clip coordinates. So right now, we're doing nothing. So I should talk about the syntax a little bit maybe. So GL is a state machine, right? And so it always has an active matrix, which is what determines the transformation that you're affecting. So to change the eye coordinate to clip coordinate transform, we need to get into projection matrix mode. So you say GL matrix mode, GL projection. And that tells it that now we're going to start messing with the projection matrix. So right now, we've just loaded the identity matrix, which does nothing. But we can modify it to say an orthographic projection. And we can tell it to, instead, let's say that our coordinate system should go from 0, 0 in the bottom left corner up to the width of the screen, say. So I can go from 0 to backing width, and then 0 to backing height. And we'll give it a near clipping plane of -1 and a far of 1. So what this should do is it should take our screen and make it so that the stuff that's actually displayed is going to be everything from 0 to the size of the screen. So if we run this, you can see we get a gray screen with a tiny, tiny little 1 pixel square in the bottom left corner, which is exactly what we should expect, right? So orthographic projection doesn't do any of the perspective transformations that I talked about. The volume we're rendering is still a cube, essentially, or some stretched out version of a cube. And is really the right thing to do if you're working with 2D data. So if you're making some 2D game and you just want to render some textures and have them fly around, GL ortho is the kind of projection you want to be using. So what I've just done here is I've changed it so that instead we're going to go from -2 up to 2, 2. And that's going to give us basically the effect of shrinking down our cube or making our space a little bit bigger. So now we see that we just have the same unit square, but it's just occupying a smaller region in the center of the screen. Okay? All right. So if you want to make things 3D, generally, you have to do that you need to tell OpenGL what kind of a frustum you want to use. So remember, frustum is the name of that truncated pyramid shape. So there's this GL frustum command, and it has sort of similar arguments. You tell it where you want the left wall of your frustum and the right wall of your frustum and the bottom and the top, and you tell it how far out you want it to go from you. So let's give it, say, -1, 1, -1, 1 from, and we need to give it a near clipping plane and a far clipping plane. So the near clipping plane says how far in front of the screen is the eye, and it determines essentially sort of the field of view of your camera. So the closer you are to your near clipping plane, the wider angle your shot's going to be. The farther away you are, the more telephoto your shot's going to be. So this is essentially sort of telling the computer how you want to set up the camera lens in this situation. So let's go with, say, 5 to 10. Why not? OK. So now let's render this and see what happens. A gray screen. Does anyone have an idea why we have a gray screen? OK. So remember how I said we have these clipping planes, right? So our unit square is being rendered at a z position of 0. And right now, everything that's closer than 5 units away from the camera is being clipped away and not drawn. So that means that in order to actually see this thing, we need to translate it back a little bit so it'll actually be within the viewing frustum of the camera. So we can use this command GL translate to tell it to move back, let's say 7, so it's sort of in the middle. And so now it'll move that unit square back so that it's actually within view. So right now, there isn't really anything that tells you that this is perspective as opposed to orthographic, because nothing has changed. So in order to actually make that obvious, let's throw in a rotation So GL rotate. And the way that this works is you give it an angle you want to rotate about. So this is in degrees. So let's say, I don't know, 30 degrees. And you need to give it an axis about which it should rotate. And this is basically a unit vector in some direction. So to demonstrate this, why don't we just rotate it about the y-axis? So if you imagine I stuck a spear in the ground and point my thumb in the direction of the tip of the spear, and I wrap my hand around it, that's the direction of the rotation. So if I do 0, 1, 0 here, we should get it so that the unit square will be shifted a little bit. So the part that's farther away will get smaller. The part that's closer will get taller. OK, and that's what we get. We can actually make this kind of cooler and throw in a little bit of animation. So let's give it a static float. K equals 0.0. And every time this method gets called, we'll increment it by, I don't know, 0.1 or something. Sine of k. So now we'll have some pretty minor animation that's going on, right? But this makes it very clear that we're dealing with a perspective transformation. If we were to do this instead with an orthographic transformation, you'd get a much different effect. Besides the fact that the clipping plane is wrong. OK. So everyone recognize the difference between these two situations? OK. So orthographic projection doesn't make any attempt to make things that are farther away look smaller. It's just projecting straight onto the frame of the screen. And this is great if you're doing CAD modeling or any kind of architectural work where you're actually really concerned about the measurements between different things. But if you want to make things look realistic, you need to use perspective. OK. So there's one more. There's a couple more things I wanted to show you. The first is that we have another basic transformation we can do, which is scaling. So we can just go ahead and say make the whole thing twice as big as it used to be. And this should make it bigger. And it does that. Let's put it back on perspective so that it's a little more interesting here. OK. So it's a lot bigger than it used to be. Now, one thing that's important to note here is that the order of operations matters. So the transformations are applied sort of in backwards order. When you say GL frustum, or when you say GL translate, that's going to translate after the scale, which happens after the rotation. So if we say, put in another translate, say we want to move it to the right one and up one, we should expect it to move the whole thing over to the right and up one, right? And it does that. Now suppose we swap the order of operations. What do you think we're going to get? Well, let's find out. So now it's moved over into the right, but it's doing the rotation about the origin. So instead of it sort of waggling over here about the center of the square, instead it's waggling over here about the edge of the square. And that's an important thing and is really easy to mess up when you're doing your own OpenGL coding. So be aware of the order of operations. It does matter. OK, so I think that's all I have for transformations. Are there any questions? OK. So that's kind of a lot to take in. So in the slides, I provided a transformations cheat sheet. These are all of the really commonly used transformation OpenGL calls that you'll be using. OK. So drawing geometry. So what I just showed you was pretty simple. It was just a rect with a texture on it. We'll talk about texturing in a minute. So let's talk about doing some more interesting geometry. So I can wander off over here for a moment. OK. So OpenGL draws, or OpenGL ES, is only capable of drawing triangles, lines, and points. OpenGL, the desktop version, can also do quads and other polygons. But really, deep down, they're all triangles anyway, so who cares? As I said earlier, the whole point is that we're leveraging this really great graphics hardware that's good at doing transformations from one coordinate system into another. So the basic idea is we define these object space vertices, send them off to the GPU, have it figure out what window coordinates those should be in, they correspond to, and then go through a process called rasterization, which takes that mathematical description of a 2D triangle and turns it into pixels that should be turned on. So the way that you do this is you give OpenGL a list of vertices, and it goes ahead and runs those vertices through the current transformation that you've defined. Along with these vertices, you can also throw in colors associated with each of them that will determine the color of pixel that gets rendered when it finally does the rasterization step. So in OpenGL, typically you'll define colors using RGBA. So that's red, green, blue, and then an alpha channel. And alpha almost always means the opacity of that particular color. So you can have things be transparent if you set it up in the proper modes to do that. The nice thing about this is that means that you don't need to worry about coloring every pixel individually. OpenGL will automatically interpolate the colors between the vertices. OK. So this is where things get a little more interesting. So you pass vertices to OpenGL and say, draw me something. It needs to know what those vertices mean. So if I hand you a bunch of points, you don't know if I want to draw just a bunch of points, or if they're triangles, or if they're lines, or whatever. So you actually need to tell it. And even if you say these are triangles, you need to tell it what kinds of triangles. So there are several different drawing modes that you can use, 3 of which are probably the most important to you guys. So the first and simplest is GL triangles. So you give it an array of triangles, or an array of vertices, sorry. We'll say these 6 vertices. And it interprets them as being sets of 3. Each set of 3 vertices defines a triangle. So 0, 1, 2 defines triangle 0. 3, 4, 5 defines triangle 1. So you might notice that I drew triangle 1 with a dotted outline. Does anyone have a theory as to why I did that? You wouldn't know unless you've done OpenGL before. Go ahead.
It's facing the opposite direction.
Yes, it's facing the opposite direction. So the order of the vertices matter. If I draw 0, 1, 2, you can see that I'm sort of drawing a counterclockwise shape. But for 3, 4, 5, it's clockwise. So this determines the facing of the triangle. So there's this right-hand rule. So if you sort of wrap your hand around in the direction of the vertice ordering, so with your right hand, if your thumb's pointing out, then it's a front-facing triangle. If your thumb's pointing in, then it's a back-facing triangle. So this is another easy thing to screw up. OK. So another common one is GL triangle fan. So what this does is it lets you basically set up something like, say, a table or a cylinder, or any time when you have a whole bunch of triangles that all share one common vertex. And it lets you sort of, well, define a fan, more or less. The reason why this is a good choice over, say, using GL triangles is because it allows the graphics hardware to reuse the transformations of vertices. So vertex 0 is used by every single triangle. And if I'm able to save having to transform vertex 0 30 times, that's going to give me a big speed up in terms of the way that my hardware performs. Similarly, we're also saving time because vertex 2 is shared between these 2 triangles and 3 between these 2 triangles. So we're able to save a lot of time by caching the results of one triangle for the next. And along that same vein, we also can do triangle strips, which are the same kind of idea, except for you always reuse the last 2 vertices. OK. So let's try to use a triangle strip to draw a tetrahedron. OK. So assume that I have vertices at these particular positions. So we'll call them tetra top, left, right, and front. And we have to start somewhere. So I'm just going to say we're going to put in our vertices in the order 0, 1, 2. And so notice that this is in a counterclockwise order, or I'm sorry, a clockwise order. So that's a backwards-facing triangle. So this is the back of the tetrahedron. So we know that in a triangle strip, the next triangle is going to use the last 2 vertices. So where should we put the next, what should be the next thing in our vertex array? bottom? Front, yes. Front's the name we're using. Yeah, so we're going to use front, well, first of all, because it's the only remaining triangle that hasn't been defined that we can use. Because if we chose top, we'd just be redefining the same triangle. And it also happens to work out. So now we're going to be defining the next triangle. So it's going to be 2, 3, and something else. We've already got 1, so we really only have one option. Or we already have right, so we only really have one option, which is going to be top, right? So we put it in top. And similarly, we only have one option left. 4 and 3 are top and front, so right is all that we have left. So this is extremely easy to mess up. Requires a lot of scratch paper and head scratching. Don't worry about it if it's not immediately obvious. If you don't have really great spatial skills, it almost always requires looking something up or trial and error a couple times. OK, so let's go to a demo on making this. Yes, question?
So the first one, 0 got reused, but here in this one, 0 didn't get reused for every one of them.
OK, so you said the first time 0 got reused, and this time we're not. So this is a triangle strip. It's not a triangle fan. So
this is a different object. I don't remember what it was.
So we're doing a triangle strip where you reuse the last 2 instead of reusing the first every time. OK. So let's see what this looks like in code. OK, how are we doing? Yeah, we're OK on time. Geometry. OK. So again, we're in the same place in our code. We're in the render method. And now we're going to find out how to actually draw shapes in OpenGL. So I've got my vertices pound defined here just to make it a little bit more clear. I got these positions on the interwebs. It knows everything. So these happen to be the positions for vertices on a tetrahedron. And I've created an array of GL floats called tetravertices, and it contains these vertices in the order that we just figured out. GL float is really just an alias for regular floats. At least it happens to be on the iPhone. This isn't necessarily true on other platforms. So to make your code as portable as possible, you should stick with using GL floats instead of floats. OK. So at the same time, we're also going to define the colors we want each of these vertices to be. So in this case, I'm going to be defining them as RGBA values, where each channel is an unsigned byte, so from 0 to 255, where 255 is maximum. And I'm going to be coloring the shapes, the vertices, so that the top is always going to be red, the right's going to be green, the left is going to be blue, and the front is going to be yellow. And the important part here is that we're consistent. The second time that the top comes up, it has to be red again, otherwise it's going to look weird. OK, so we defined a couple arrays, and now we need to tell OpenGL about them. So I showed you this before. We can do some simple animations if we just keep track of what time it is. So we need to tell OpenGL about these arrays. And the way we do that is with these GL something pointer methods. So GL Vertex Pointer will tell OpenGL that we have an array of vertices where each vertex is of size something. This is going to be size 3 because we're giving it 3-dimensional vertices. If you do 2, you can do 2D graphics a little bit more easily. But generally, it's going to be 3. And then you tell it what type of data they are. In this case, we're representing the vertices as floating point values. So you tell it GL float. Then you tell it stride size. This has to do more if you're using interleaved arrays. Don't worry about it. Just set it to 0. And then finally, you give it the pointer to the actual array. And so that registers with the state machine. When I ask for a vertex array, grab it from this memory location. And so now that we have that pointer set up, the next line is we actually tell OpenGL, yes, it's OK to use that vertex pointer. It's set to something reasonable. So when you start doing drawing, make sure you read from that pointer. And the color pointer is almost identical. We're again just telling it, here's a color pointer. I'm registering this with the OpenGL state machine. And it's going to have 4 elements per color because it's RGBA. If you do any other number on the iPhone, I'm pretty sure it won't work. At least I haven't seen it work. You can't do RGB colors. So they need to be RGBA. And unsigned byte is great just because it's compact and has just as much data as any other type. Again, stride size we're going to ignore, and then we finally give it the actual array. And we also register it in the same way. You say GL enable client state, GL color array, and that tells it to actually use the color array that's there. So the last thing that we need to do here is we need to actually draw the array. So that's a simple, or draw the polyhedron. That's a simple call to this GL draw arrays method function. So what it does is it grabs all of the currently activated arrays. So we have the vertex pointer and the color pointer in this case. So we have two arrays that it's actually going to be reading from. And we tell it to draw a triangle strip. Let's see what the arguments here are. A triangle strip starting from the 0th element. And it has a total of 6 vertices that it needs to care about. OK? So let's see what this looks like. Is that going to run? Oh, simulator's still going. OK, so it does what we want it to, because I made sure it did. So we're drawing a tetrahedron where every vertex has a specified color, and we're properly displaying them in the right order to make sure that all the triangles are facing out, and it makes a tetrahedron. OK, so this is pretty cool, but it's not nearly awesome enough. Yes, question?
They're not facing out.
Say again?
What happens if they're facing in?
OK, so the question is, what happens if you aren't careful and you have triangles that are facing the wrong direction? So I will show you the horrible truth.
They get drawn from the wrong side?
Yeah, so by default, they will draw happily and it will look weird. For the purposes of the demo, I'm not talking about depth testing. So this is what happens if you're not careful with it. These are still facing the right direction, but I'm not paying attention to the depths of the triangles, so they're just being drawn in the order they're defined. So I'm actually keeping track of whether, if it's a backwards-facing triangle, I don't draw it. Don't worry about it. Basically, you want them to be facing outwards in order for a lot of the later on OpenGL code to actually work. OK. So let's make sure this is working again before I start messing with it. OK. So we've got a nice-looking rotating tetrahedron. It's a little small, though, so let's make it bigger. So we can throw in, say, scale it up by a factor of 3. Cool. It's bigger. And say we want to translate it off to the left a little bit. We can do that, too. It works. Now, if you want to draw more than one thing, this approach isn't really good enough. And the reason is because when I do this translate F and rotate and scale, I'm messing up the transformation matrices that I've set up before, right? So you need to have a way to sort of save the state of the transformation and then later get it back so that I can draw this one triangle up and to the left and draw another triangle down and to the right or something like that without having them mess with each other's positioning. And so there's these two functions called GL push matrix and GL pop matrix. And so what this does is it defines a transformation stack where you push the matrix, you save the existing transformation, and then when you pop it, you recover it. So you don't need to worry about messing with other people's transformations as long as you're within your own sort of stack window. So using this, we can really easily add 2 more of these triangle things that have their own different transformations. So one's going to be sort of up and to the right, and one's going to be kind of down and to the right. And they do different stuff. And notice since we don't actually have to change any of the geometry, we can just reuse the same exact call to draw arrays. But now it's going to be drawn in a different place because the transformation matrix is different. So now we get 3 of these things, and they're awesome and look cool. Does anyone disagree? OK. So any questions on geometry and using transformations with them? All right, cool. So again, I've provided a sort of a little geometry cheat sheet to cover all of the pertinent lines of code that produce that demo I just showed you. Yeah, I'll let you look at it offline. Okay, so the last thing that I really wanted to talk about was using texture mapping. So those shapes were pretty cool, but they were kind of abstract and not very interesting to look at in terms of colorfulness. So it'd be nice if we could make things look a little more realistic, and this is where texture mapping comes in. And this is particularly important if you want to make something that's nice looking on the iPhone. So basically, the idea is that instead of coloring pixels based on the colors of the vertices on the corners of the triangles, we're going to instead color them according to some image that's been stored in memory. Generally, textures are always 2D. You can do 3D textures. I don't know if that's actually supported in OpenGL ES, but even on desktop machines, I rarely see 3D textures used. But the basic way that you work with it is instead of giving vertices colors, you give them texture coordinates that say where in this texture image they should start grabbing their color data. So if I draw a triangle and I want it to look like, say, the bottom half of this thing, I'm going to say one of the vertices should have texture coordinate 0, 0, one should have 0, 1, and one should have a 1, 1. And so this is parameterized in this UV space, where the U coordinate is sort of like the X coordinate of the image, and the V coordinate is the Y coordinate of the image, where the top left is the origin. And it goes to 1, 1. This is, again, regardless of whether or not the aspect ratio of the image is a perfect square. Okay, so you might think that you can use these and say, great, I'm going to have one texture for every object in my game. The problem is that swapping textures is really expensive. So almost always what you'll do is you'll make what's called a texture atlas, where you have one big texture map with lots of little bits in it for different things. So you'll have, your I don't know, hockey puck would be some part of it, and the table will be some other big chunk of it. And they can all share the same texture file, and that way you don't have to worry about swapping in and out textures all the time. And that way you have the texture coordinates mapped to small regions inside. So let's say we wanted to texture our tetrahedron with this texture. Well, all we really need to do is figure out the texture coordinates that correspond to each of the vertices. So this can be pretty easy. We'll say this point in the texture is going to be this corner, this point's this corner, that point's that corner. Great, everyone wins, right? The catch is, what about the top one? What should the texture coordinate of this vertex be? Well, there's not really a good answer, because you really want it to be all three, right? In order for this thing to work well, it needs to be this point for this triangle, so that's, I don't know, one of these faces, say, and this point for this triangle, and that point for that triangle, right? So it needs to have different UV coordinates depending on which triangle it's defining. And that's sort of annoying, because that means we can't really use the cool triangle strip trick that we used before. Now we have to actually draw these things as separate triangles every time. If you're careful, you can maybe get away with a couple of the triangles and triangle strips, but it's probably not worth the effort. So in the demo that I'm about to do, I've given these texture coordinates some particular names that'll make it easier to actually code this thing up. So there's going to be a one-to-one correspondence where the left vertex is going to have texture coordinate 2, the right vertex is going to have texture coordinate 3, and the top vertex is going to kind of have 3 texture coordinates, which is kind of weird, but there's nothing you can do about it. OK. So any questions before we head off to the demo? Cool. OK, so before we get into applying those texture coordinates, I want to tell you really quick how to set up a texture. This is normally a really big pain, but luckily we can get away with stealing Apple's demo code, and it makes everything much easier. So this piece of code you're looking at right here, this is in the initialization method for the ES1 renderer. This is, again, part of the basic template program that the OpenGL ES applications give you. And I've added this bit at the end here. So there's this class called Pvr Texture, which is part of the Pvr Texture demo sample code, I believe. I forgot the exact name. But it provides this really great interface where you just give it a path, and it gives you back a texture object that you can bind onto to do any drawing with it. So it's really straightforward. You build the path. I have a file called d4.pvrtc. I should probably tell you what this file thing is. Basically, it's a special image format that's really well optimized for doing OpenGL rendering. You can create them using this thing called texture tool with the command line argument that I provide in the cheat sheet. But they're easy to make. You just need to run one thing on the command line. So anyway, so I created this file, and I loaded in using the Pvr Texture loader class. And now I need to bind it to the OpenGL context. So the OpenGL state machine needs to know what texture it's going to be reading. And the way it does that is you just say GL bind texture, what kind of texture it is. It's a 2D texture. And then the name of the texture, which is basically just like an ID number. And this is what the Pvr texture object gives us. Okay? So these next 5 or so lines set up a whole bunch of parameters that treat the way that textures are interpreted. You need to do all of these, otherwise it won't render properly. For the most part, this will do what you want. What these parameters mean really quick. How does it deal with the Magnification Filter? Is that right? Is how it handles textures that are smaller than they are as they're defined. So if you have a really big texture and it's showing in 10 pixels on the screen, how do you want to handle the interpolation? The easiest thing is linear, where it just sort of scales down the image linearly. You can also do, say, nearest neighbor or something like that instead. The magnification filter is the opposite. How does it treat textures that are being displayed on the screen bigger than they are in memory? So again, you can do things like linear or nearest neighbor. The anisotropy limit basically says it has something to do with the way that textures are rendered when they're on severe off-axis stuff. I would refer you to the OpenGL documentation on that one. And then finally, we have the wrapping procedures. So what this is saying is, if you define texture coordinates that are greater than 1, how does it treat that? So if you say clamp, it'll just sort of pretend that any coordinate greater than 1 is 1. You can also do things like, I forgot what it's called, but there's one where it repeats, like it just tiles the whole space with textures. I think those are the main ones that you'll ever use. But you can tell it how you want it to behave in both S and T. I guess I called them U and V before, but either one works. OK, so now we have a texture set up. Let's actually use it. So if you go back down to the render method here, I've redefined the way that we're declaring this tetrahedron. It's now I'm doing with 4 triangles instead of 1 triangle strip. I'm sorry that I have to sort of make all of these things, pre-baked demos and not typing live code, but doing this in OpenGL is really hard and super easy to mess up. So actually typing in these numbers or even these macros would still probably go horribly wrong. So forgive me for that. But trust me, if you set these up and sit down on a piece of paper, it'll make sense and it'll come out this way. So the next thing that I do is I set up the texture coordinate array. And so this is pretty much exactly the same way that we handled this for the color array. We just have, for every vertex up here, we have a corresponding texture coordinate down here that matches those mappings that I talked about before. So the 1 texture coordinate always corresponds to top. The 2 or the 3 coordinate always corresponds to right. The 2 coordinate always corresponds to left. And you just have to make sure they all line up and work well. This is another place where it's easy to mess things up. But assuming you did it right, then you can go on and actually let OpenGL know that you would like to render this thing. So you do it in pretty much the same way that we did with colors and vertices. You give it a texture coordinate pointer, and it is of dimension 2, which makes sense. If you're using 3D textures, it would be 3, and you'd give it 3 coordinates per vertex. There are going to be floats. We're not going to worry about stride, and we're giving it the texture coordinate array. And then finally, after that, we tell OpenGL, yes, we would like to use textures. Go ahead. And that's the GL enable 2D textures. Then after that, the drawing is exactly the same as it was before, except for now we're doing triangles mode, but it's basically the same. And when we run it, we now get this. So we now have textured tetrahedrons, and they're awesome. OK. So any questions on textures? OK. So here's our texture cheat. Everything's cool. All right. So now here's our texture cheat sheet. This one is, I would say, significantly more complicated to actually get set up and running. The first 6 or so lines there make everything tremendously more easy. If you try to load in a PNG texture, you have to go through a lot more hoops, and it's slower anyway in terms of performance. So I would strongly recommend just using the Apple demo code. It's great. OK. So starting to wrap up here, I guess. A couple other details. So the first one is OpenGL ES1 versus ES2. So when you start a new OpenGL ES template project in Xcode, it will sort of give you both options. I would strongly recommend against using OpenGL ES2 if this lecture was at all helpful to you. And the reason why is that OpenGL ES2 has a drastically different architecture. It's based on writing shading language stuff. So you have to write these OpenGL shaders that allow you to customize the way that the rendering pipeline works. And this is great if you want to do something wacky and weird that isn't drawing triangles on a screen. But if you want to draw triangles on a screen, figuring out how to do it is a lot harder. So if you just want to do normal, I'm making a game and want to show cool geometry, use OpenGL ES1. It's also important because OpenGL ES2 isn't available on older iPhones and older iPods. So if you want to be portable on all those devices, make sure you use ES1. OK. So the last thing here is if you want to know more, I mean, this lecture is really just the surface. There's so much more you need to know if you really want to get into this stuff. Places I'd suggest looking. The Apple OpenGL programming guide is great. It has demarcations for things that only work on the iPhone and only work on OS X. The OpenGL Redbook is great. That makes heavy use of the glut and glue libraries for desktop stuff. So that might not be quite as applicable to iPhone programming, but is still a great resource for sort of foundational knowledge of how OpenGL works. The internet's great once you know what you're doing. And here at Stanford, we have 2 sort of introductory graphics classes, CS 148 and 248. And those will give you a good foundation in a lot of the math that goes behind all of these OpenGL calls. So once you've done that, everything becomes gloriously clear. So in particular, when you're looking at these things, topics of interest sort of in order of when you're going to want to use them. Frame buffers, really quick, those are the things that sets up memory for where you're actually going to be drawing these pixels at the end. Depth testing, I sort of touched on that earlier. If you have anything in front of anything else, you probably care about that, because otherwise it's just going to draw whatever's newest on top. Backface culling is mostly a optimization trick so that you don't have to draw anything that's being covered up by other stuff. Animation, not really part of OpenGL, really. It's more something that you wrap around it. So we sort of touched on that with the static T value that increases every time it renders, but that's sort of a cheap hack. There are probably better ways of doing it, and I'd suggest asking the internet how. Transparency and blending is cool. I'm pretty sure that if you wanted to use UIKit elements with OpenGL, things get hairy. Is that right, Josh?
You can put a UI view on top of the GL view.
OK, so Josh says it's not too bad to put a UIKit view on top of.
Things down because we can't take the fast path that goes directly to the screen. It'll basically render to an off screen and then compile.
I see. So what he's saying is that when you do other UIKit stuff, it ends up having to render to an off-screen buffer and then composite them, which slows things down a lot. So be careful if you're going to be trying to mix and match between the two things. And lighting and shading is also cool. I don't know how realistic it is on a mobile device like the iPhone, But if you're doing desktop applications, lighting and shading is great too. So I think that's all I got. Any questions? It's probably not worth putting you up here for 10 minutes.
No reason to ruin a good thing.
Yeah. OK. So thanks, everyone. Good luck on the final projects.
For more, please visit us at stanford.edu.